yesterday in like a semi-different but kind of the same way. So we're going to think back to yesterday, previous lesson, and we talked about if you were charged 12% interest on your credit card, what happened when you took interest a different number of times. So let's review what these words mean. Annual, if you take interest annually, how many times a year is that? Semi-annually would be? Quarterly, 4 times, and monthly would be 12. So we'll divide up here in a minute, but let's talk about annually. Let's get us set up. If we took interest, if we had 12% interest and we took it once a year, that means that you were going to take 12% interest that one time. Correct? Remember that from yesterday? So say we had $1,000 and we just want to know after 1 year, that's it, not a lot of years, but 1 year, if you didn't pay off your credit card, how much money would you owe the credit card company? So we're going to write an expression. We'll just do y equals 1,000, and we'll go in your parentheses here if you have 12% interest. 1.12. Okay, so we're at 12% interest, and we're just looking for 1 year. You take interest one time, so you put an exponent of 1. Right, this is based off of that formula we discovered yesterday. Now type that into your calculator. How much money would you owe the credit card company after 1 year if you didn't pay interest and they charged you 12%? How much money? $1,120. All right, that's actually kind of a lot if you think about it. Like you don't pay interest for a year, and you not only owe $1,000, now you owe $120. $120 is to me a lot of money. I don't know if you guys think that's a lot, but I want $120. Now we took interest twice a year. How much interest would you be taking each time? 6%. Right? So you have 12% for the year, but if you take it twice, that's 6%. So what expression would you write here? You'd have 1,000 times 1.06. And if you take interest twice a year, what would be your exponent? 2. We had 2 times 1 because it's 1 year. So we'll just put 2 there. You could put the times 1 if you wanted, but then 1 won't change it. All right, well, how much money would you owe the credit card company if they took interest twice a year? Yep, 0.60. So it's a little bit more. It's not a ton more, but $3.60 added up. That's like just like a scoop of ice cream somewhere. It matters. What about quarterly? How much interest would you be charged every time if you take it 4 times a year? 3%. All right. So we adjust our equation again. This time for 3% interest. So you take interest on your $1,000, 1.03, and what would your exponent here be? 4, right? Because you take interest 4 times in that 1 year. And how much money, Jamie?
1,125.51.
Yes. Good. Got a lot of numbers today, so I don't remember them all. All right, so it's going up a little, right? Do you remember yesterday how we said the more times you take interest, your account balance goes up? So finally, if I took interest monthly, what percent would you be charged every month? 1%. All right, so your equation here would be 1,000 times 1.01 to the 12th, because you're taking interest 12 times. And tell me what you would owe the credit card company. $1,000? Yeah, 0.83. All right, so it's going up a little bit, right? Well, there's this accountant. So it's a dastardly accountant, evil, cruel, wicked. This wicked guy works at the credit card company. And remember, credit card companies want to make money. That is the point of being a business. They want a profit. And he notices that the more frequently they charge interest, the more money they make, right? As we went up that table, the money got higher. So, sure, if this starts going up only like $3 and $1.50 or so, that's not a lot, right? But think about, you're not just one person. Credit card companies have tens of thousands of customers. So like $3.60 for tens of thousands of customers really starts to add up. So his thought is, okay, how frequently do I have to charge this 12% interest to get to 1,128? Because this accountant wants to make a lot of money. So we're trying to figure out how often should we take interest to get to that amount of money. So let's talk about weekly here. How many weeks are in a year? 52. All right, so if we took interest 52 times a year on 12%, can you figure out what the decimal is for the interest rate they have to charge every week? Take 12% divided by 52. Does it give you anything nice? I don't even remember. Let's see, 0.12 divided by 52. That's kind of yucky. So why don't we leave this as a fraction when we put this in our table? So we'll say, okay, we'll just do 0.12 over 52. That's going to be our interest rate. So what would be our expression here? What would you type into your calculator to find how much money you'd get if you charge weekly? 1,000 times 1 plus, yeah, 0.12 over 52. And what would be your exponent? 52. All right, so type that into your calculator here. How much money would this accountant get? Or how much money would the credit card company get for charging interest that often? And then we'll speed it up a little bit. How much money? 0.34. Okay, so we went up again. Now, if I took interest daily, how much would that be? How many times a year? 365. Okay, what if you took interest hourly? How many hours are in a year? I know minutes. 8,760. And I know minutes only because of the Rent song.
Yeah.
525,600. It's called Seasons of Love. I sang it in 6th grade show choir. And then I sang it in like a church choir thing a few years ago. But 525,000, that's the first line of the song, by the way. First thing you say. How do you measure a year? Now, let's break it up. I can like break out into the song right now. I'm going to spare you that. Google it in a little bit. Yeah. So I want these two rows. I only sing in ensemble. I don't sing solos. I want you to find the amount of money when you compound interest daily. I would like these two rows to find the interest when you compound it hourly. And I would like this row to find the interest when you compound it by the minute. All right, that way I don't have to write all those numbers and you know the pattern by now. So since you know the pattern, I want you to just type in yours and then we'll get the interest. We all have to learn the song, but Jillian knew what I was talking about, though. It's like a good trivia fact, though. They should use that for wits and wagers, see if anyone knows. Everyone will know. Only people who know random music. All right, my daily folks. If you compound interest 365 times a year, Bobby, how much money would you have? $1,127.47. And 47 cents, that's right. All right, so it only went up 13 cents there. A little bit. How about my hourly folks? How much would you have? Over the next two rows. How much money would you get for hourly compounding? And 50 cents. Yeah, so we went up 3 cents, so it went up a little bit. We're getting there. What about my folks who did minutely compounding? How much money would you owe the credit card company? Last row, did you type it in? Yours was a very quiet row. 1,100. $27.50. Uh-oh, what happened? What? You're just saying the next part of my little spiel here. What? The accountant's tiny, cold, little heart skipped a beat.
Accountants have hearts.
There doesn't seem to be a way, or at least not yet, to reach 1,128. That was this dastardly accountant's goal. And we kind of, like, stalled out at 1,128. 50 cents. So he comes up with this idea. Okay, minutely didn't work. But if I could charge interest all the time. Well, we could do seconds, but even more than seconds. What if we could charge interest all the time? Like every millisecond on the millisecond. Beyond that. Surely we can compound interest infinite number of times a year. And if I can compound interest infinitely, I could make infinite dollars. Right? It would make sense, right? If I could charge interest all the time, I can make a ton of money. So let's break this down to a really simple case. Okay? And we'll break this up again in a minute here to speed it up. Let's just try a new scenario. You get 100% interest on this credit card. So in reality, that would be horrible because if you didn't pay your bill, you would owe 100% of what you owe. But let's pretend we have a $1 charge. Right? Use your credit card for a $1 charge. You have 100% interest, and you're just doing this for a year. Okay? So we are technically using the formula that we came up with yesterday. The one that talks about the principal, the rate, the number of times you compound. But since we're using ones for everything, I broke it down into this nice, simple version of the formula. 1 plus 1 over n to the n power. So if I took interest, we're just going to see a pattern here. These times, 10 times, 1,000 times, 10,000 times. We want to know what happens to the money you would owe. So let's do 10 together and then we'll break it up so that we can write a little bit less. So if I take interest 10 times, I'm going to put in 10 in for n. So you would have 1 plus 1 over 10 to the 10th power. I'm going to evaluate. Oh, is there something on the wall? Should we do it? Go for it, Jamie.
Yeah.
Here, Tom.
They all have my desk.
There was a bug. We had to have a bug break.
Huzzah!
Thank you. I saved a lot of bugs this year. Was it a fly?
No, it was those long sticky dudes.
Oh, a centipede?
No,
Oh,
okay. It was a
Okay,
centipede. I'd be out.
a few years ago, I think the year I had some sophomores, so some of the sophomores who are now seniors had them in algebra 2. I was in my old room, and I killed a centipede, and oh my gosh, that was like the biggest thing. We then they wanted to have a funeral, and every day, the whole rest of the year, they would draw a centipede with a tombstone on my board, and they still ask me about killing the centipede. Like, seriously. This happened in, like, September. Every day. So, like, people like Mike Wagner, Mason Blair, I don't know if you know that. But, ask them about the centipede. Alright. Type this into your calculator. To 5 decimal places. How much money would you owe on that dollar if they charged you interest 10 times a year for a year? How much money here?
It is
Go ahead, Bobby.
$2.59.
Yeah, we're going to 5 decimal places.
59374.
Alright, good. Now, let's speed this up a little bit. If we took interest 1,000, 10,000, 100,000, and a million times. So let's break up into rows again. I know. Well, you only have to do it once. You just have to copy down the rest of the numbers. So let's have this row right here do the 1,000. You guys do 10,000, so the 8th row. These 2 rows can do 100,000, and you guys can do the million. So you're going to put that number in for n. So example, I'll just write the 10,000 up here, but it's a lot of zeros, so it saves me a little bit of writing. You're going to put all those zeros in, type it into your calculator, and go to 5 decimal places. We should start to discover a pattern here in just a minute, once we get all those numbers. Just do yours. You don't have to do the rest. We'll copy them down in a minute. Lots of zeros. My 1,000 group, what would be the number evaluated to 5 decimal places? 692. Good. So 2.71692. If you were not in that row, I would write that number down under 1,000. 2.71692. What about if you were in my 10,000 row? What decimal did you get?
2.718.
Yeah, 15. So 2.71815. That was what you would owe. So about $2.07. if you had this was your credit card. What about my rows for 100,000 times of interest, Jamie?
2.71826.
All right, 2.71826. And my 1 million row? What do you have, KJ?
2.71826.
Yes. All right, well, what are we noticing here?
It's money.
It gets higher, but it doesn't get higher by very much. I mean, we went like 2.6, 2.8. So, does this dastardly accountant scheme seem to work? No, you're not going to get to an infinite number of money. It looks like we're kind of hitting a wall here. So if we flip our paper over, it says that it turns out that there is a limit to how much interest the credit card company can earn, despite taking interest 1,000,000 times a year. Now, the idea of a limit is a really fancy concept, like calculus level fancy. You will do limits at the end of pre-calculus, but this is as much, we don't really have the tools yet to talk about limits. So it's a really fancy concept, but the idea of a limit is that there's a point where you can't quite reach it. Now, what do we know? It starts with an A that we've talked about, what you get really close to but can't quite reach. And asymptote. So we'll see like an example that's kind of the same idea here, but a little bit different. But basically, as x approaches infinity, so as we make through this table, if we made these numbers bigger and bigger and bigger and bigger towards infinity, the numbers down here that we evaluate get close to Bobby's favorite number, E. E is about 2.718. That's what we were getting. If you look here, we have 2.718, 2.718, 2.718. We got real close to E. Now, E, well, since that's very unfortunate for the accountant. So it seems that we can't make an infinite number of amount of money off of interest. So let's visualize what's happening with this graph here. So I want you to graph in your calculators y equals 1 plus 1 over x to the x. That was the basic formula that we just did. And then it gives you some window settings that we will set up here. So we'll put our parentheses, we'll make our fraction. Now when we make our window, what does it have for the x's? 0 to, was it 100? Yes, so 0 to 100, and what's the scale? 10? What about our y scale? What does that say? 0 to 5. Alright, so if you make this graph here, that's the picture you kind of see. So it does look like a logarithmic function that we've been working with. But let's graph that here real quick, and then we will look at it. So it kind of looks like that. Now on your calculator, we have used the trace feature before. But this time we're not going to hit second trace. We're not finding a maximum or anything. I just want you to hit trace. Okay. Now if I hit trace and I scroll to the right here, I want you to watch the y values on your graph. As you keep clicking to the right, what's happening to those y values? We're getting to 2.7. Oh, I lost it. And it's just going and going and going. Does it look like it's ever going to get higher than a certain value? What does it look like our graph is approaching? It has an asymptote. That asymptote is at the letter, or not the letter, the number E. So this graph here approaches, I can't spell and talk at the same name, A-P-P-R-O-A-C-H, approaches the line y equals E, right? You have that asymptote at y equals E, and my graph is getting really close to it, but it's not going to get there. So let's finish up here. Just like the number pi, E is irrational. That means like it doesn't stop. We can't write it as a fraction. If we evaluated E to 9 decimal places, it would look like this. 2.71828, and it would just go dot, dot, dot. Now, in the last class, yes, it looks like there's a pattern, 1828. However, since it's irrational, I don't know where, but that pattern must end eventually, because otherwise it would be a repeating decimal, like 0.3 repeating, and we could write it as a fraction. So somewhere that pattern stops, and there's another number thrown in. But for now, that's 9 decimal places. So E is that value. All right, now, what we have here is E is used in situations where we have continuous growth. So, for example, like babies being born and people dying. Babies are not born like clockwork, right? People don't die on a schedule. It's not like, oh, 1 hour every day someone's born, or every hour someone dies. It just happens continuously. Or in the half-life of a carbon or of an organic compound. Have you heard of carbon dating, history, science? All right, things are always decaying constantly. Or growing, your body. You don't grow like, oh, half a centimeter every hour. You grow continuously. So what that brings us to is this special formula here. I call it the A-Kurt formula. That formula is a complement to this formula that we came up with yesterday. And we are going to talk a little bit more tomorrow about when you would use either formula and what they're good for. Okay, so the PERT formula that we just kind of figured out today is for continuously growing and continuously compounding situations. All right? All right, so that is what I have for you today because we have a short